what I wanted to teach was, can we apply a PID controller to a mobile robot is a question that I get most. And the answer is no, because for a manipulator, suppose 6-link manipulator, there were 6 motors, 6 desired angles, and every motor had one independent desired angle. So every motor could be controlled specific independently. Now mobile robot, I need to control X, I need to control Y, I need to control theta. I can control a linear speed by acceleration and brake. I can control angular speed by the steering. Or in a differential wheel drive robot, you can control V left and V right. And you know that, of course, linear speed is V left plus V right divided by 2, and omega is equal to V right minus V left. So I have a 3 degree of freedom and I've got a 2 degree of freedom control. The number of control variables are lesser than the number of variables that need to be controlled. So there's a problem. The other problem is every variable does not control an independent variable, and that's pretty bad. And because that's bad, let me do something. The bare minimal problem that you could think of is, so let's take in a mobile robot, and that's usually my first example when you are doing the labs. I want the robot to turn and face the goal. Now it's simple. So now it's basically pretty much simple, and it's basically pretty much simple because I have one variable theta t to control, and there's one angular speed by which I'll control. So it basically becomes a manipulator. So my error is theta desired minus theta t, and theta desired is theta goal minus theta is equal to a tan 2 goal y minus y goal x minus x. Now, I always write down this thing. Of course, when you're programming, then you need to make sure this is between minus pi to pi. And the only way to make sure that it's minus pi to pi, to write down this is okay, but in reality what happens is et is equal to a tan 2 sine theta e cos theta e, and where this is theta e. So this ensures that this range is followed. That's what you do every time you take angle differences. Angle cannot be directly taken the difference of. Otherwise, minus pi minus minus pi becomes minus 2 pi, which is 0. Of course, minus 2 pi and 0 are the same things. But then whenever you need to access angles and you're not doing it by sines and cos, you need to ensure that all angle arithmetic are between minus pi to pi. So you use this dummy function, which just corrects for the range. Otherwise, if theta des is equal to minus pi and theta t is equal to minus pi, then et or theta e becomes Oops, bad example. Plus pi. So don't move by a very large speed, negative, because this is actually zero. This is what ensures that the ranges are taken care of. But then, of course, this is not the problem. I just took this one up. The actual problem is moving the robot. So let's complicate the example and let us say that this is my goal and I need to turn in the direction of the goal and I need to travel. So this should be my path. How do I do that? So again, I measure a speed, I measure error in terms of both angular speed as well as linear speed. So I say my ET is equal to angle because we've already seen it. So theta desired or theta goal minus theta t. These are two angles, of course, and my linear distance is the same way. So if I had a smaller problem that you just have to reach to the goal, you would have said V is equal to Kp times the error. The error would have been this distance. So that's the distance between goal and my current agent minus the radius of the robot. And let's add this to here. So that becomes distance between goal and my current position Q minus the radius of the robot. That's my error. And of course, my V omega becomes Kp times Et plus I times integral of Et plus derivative of Et. That's when the robot will actually move towards this goal. You'll have to check the constants, you'll have to set them up appropriately. That's again different from the, so basically what happens is when this error becomes zero, the robot actually stops at the goal, and when this error becomes zero, when the robot is facing the goal, the robot only travels with a linear speed because of this error. So you get a nice motion directly to goal. That's exactly what I drew over here. Coming on to the actual problem, so I've got a map like this, and somebody told me that this is the path to take, and at any general point of time, this is where my robot is. Now we define this error, which is called as a cross-track error, and you basically use Et is equal to current cross-track error. So the least distance between your position and the trajectory, that will be the perpendicular. You can actually compute it extremely fast because you need to do local search as you travel, and if your algorithm is in the form of these lines, then you can always get your geometric formulas to calculate the cross-track error. It's signed, so this is negative and this is positive. So I'm here, I move over here, here I move over here. So V is proportional to the angular speed is proportional to cross-track error, or can also add I and D. And sometimes you say that the speed is constant, and sometimes you say that if the error is extremely large, then the robot should slow. So V can also be proportional to the same cross-track error. So you actually got one error that controls both v and omega. So speed is small if your cross-track error is small, and v is inversely proportional to cross-track error. And here it is not signed, so it's absolute value. So you say when the cross-track error absolute value is large, v is small, and when the cross-track error is small, then you basically travel at the highest speed. That's another way to do that. The essential thing is that the control, so the PID is over this omega, or the angular speed is controlled by the PID controller, where you take the cross-track error as a metric. There is a problem with the cross-track error as well, that you actually go upon, you say that cross-track error is large, and because the cross-track error is large, you want to continuously go here, but you don't take the angles into the consideration, that you should also reach the goal with certain kind of an angle. So if I reach here, the cross-track error is 0, it's very happy, while the robot should actually be looking at over here. So there is another model for control, and that's the same way we fuse the deliberative and the reactive approaches. So I'll not repeat that except for make a mention. So that's my robot at every point of time. Now I need to be angle conscious, because if I'm at the trajectory with the correct angle, that's a problem. So what I do is I take a virtual leader, and my error is with respect to the virtual leader. So let's write down the same modeling again. My error is let's go v first and then omega. So distance between the virtual leader and my current position, and this is theta e, where theta e is the angle between virtual leader and myself minus my current angle. It's always a tan 2 sine of this and cos of this, so I don't write it down always. Theta virtual leader y minus q minus my y, comma, virtual leader x minus my current x, which looks interesting. Now the only problem is that virtual leader moves with time. So let the virtual leader go like this, 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 like this. The robot is always following the virtual leader. So when the virtual leader is here, the robot would try to follow it here, it will follow it here, they'll follow it here, it will follow it here, with the follow it here, with the follow it. So when the virtual leader is here, then the robot would try to go here. When it's here, it will try to go here, and so on and so forth. So the virtual leader could be just a simulation program that follows this trajectory. It can take sharp turn, it can travel with whatever speed you want, and it can do everything which is possible. So the virtual leader has absolutely no constraints. Now, again, you don't want to make the distance between the virtual leader and the robot very fast. So whenever the distance between the virtual leader and the robot goes more than the distance, the virtual leader slows or stops. And whenever the virtual leader and the robot have too little distance, then the virtual leader moves faster or it travels after a distance. So let me write down as a rule, the virtual is always at a distance d ahead of the robot. So my only inputs are this, and these three are known by the localization system. So I know all these because these are known because of the localization system, or my localization system, it at every point of time tells me what my position is. So again, for the last time, summarizing what we discussed so far, which forms the backbone of the simulations to be discussed next. When the robot comes into our lab, we take it out. The first thing that it does is that it makes in a map using a technique called as SLAM, which is simultaneous localization and mapping. It calculates its own position based on whatever little it knows from the map. It looks at a television and it says that I know this television is at 553, all the corners. I'm seeing this corners at 225, similarly with all the corners. So what should be my position? It guesses, it solves the optimization problem. It always knows its own position. And then using the position it calculates new things, new corners. The second thing that it does is that it makes a roadmap using which it can do deliberative planning, and using its onboard sensors, it does a potential field on a new map which also has moving people called as a local map. So global localization, approximate position, local level localization, the specific position. Similarly, global map, only static. Local map, static plus local plus dynamic people moving around. So it makes him, using its onboard sensors, a local map, and using potential field that avoids them, and the two are related to each other. And finally, what it does is that eventually the motors need to be controlled, which is my control algorithm. So using the control algorithm, I decide how much the motors need to be operated, what reference speeds needs to be given to the motors, or what linear and angular speed needs to be given. And that's exactly what we do. So we read the sensors, we calculate the V and omega, and finally we just need to give to the manufacturers libraries a sample V and omega, a sample linear and angular speed, and my robot will end up hopefully moving with the same speed. Along with that, some unavoidable errors, unfortunately.